Good morning, dear colleagues. I'm Weili Zhang from University of Electronic Science and Lasers for imaging application. Okay, this is the outline for part. First, to the introduction part. Okay, as we know, disorder exists widely in nature and man-made structures. You can see from these pictures, uh, disorder exists fiber, photonic crystals, and biomaterials. Generally speaking, disorders are harmful in optics because they cause strong scattering of light, while in some special applications like random lasing and speckle-related images, disorder can be very useful. Let's see how light transmission in different medium. In strongly scattered medium, like three-dimensional or two-dimensional disordered structures, light is scattered in every direction. And you can see there are many channels of light, and the loss is large. Well, in ideal waveguide, like multimode fibers, if there's no scattering considered, light can be confined in the core of the fiber or waveguide by total internal reflection. And this kind of waveguide support transfer mode with field distributions like this, different transfer mode. Well, actually, in real applications, there is always existing macrobending or defect in multimode fibers. So this will cause mode crosstalk and mode interference, and the multimode fiber finally become speckle patterns with random distributions like this. In this case, multimode fiber can be treated as a kind of weakly scattered matter. They provide a proper number of channels for light travel. This number is not, so it's still under control. Secondly, light transmission in the multimode fiber is almost lossless, and the output is directionally. Such kind of waveguide provide a good platform for spatial light control. Here shows some topical applications based on multimode fiber, like spatial mode wavelength division multiplexing in communications. This is very helpful to enhance the transmission capacity of the system, and also spatial temporal mode locking. Report uh, they can be used in microprocessing and light manipulation. Another character of a multimode fiber is the output patterns. It's very sensitive to the wavelengths, so we to build high resolution spectrometers. Besides, recently, multimode fiber has also been used as endoscopies for imaging application. They can achieve high resolution immersion images. Sorry, there's noise. High resolution images with, with much higher resolution than fiber bundles used in currently used endoscope. Okay, let's move to the second part, control of laser output. First, I'd like to introduce the kind of lasers we use for imaging application. As we know, in conventional lasers, there is regular mirrors to form this regular cavity support standing wave mode with equal wavelength separations. and their output is directionally. Well, in random lasers, the feedback loop do not need mirrors. It is formed by of light in disordered mediums. So localized mode can be formed. They distributed randomly in the medium, and their wavelengths distributed randomly in the spectrum. The combination of random lasers and optical fibers generate concept random fiber lasers and fiber random lasers. This kind of laser inherent advantage of both and random lasers. The advantage of both fiber lasers and random lasers. For example, they have a good output character like high beam quality, high quality, and high efficiency. Besides, their structure is very simple and they have a large lens volume ratio. This is for heat dissipation and can save clean components to facilitate high power and high spatial wavelength operation. And this kind of laser provides an open structure of laser with high degree of control freedom. Here shows a milestone work on random fiber lasers. It's proposed by Torres Group in 2010. Here is a single mode fiber. They use Rayleigh scattering to provide random distributed feedback, and they use to provide the gain. When the pump is strong enough, they can get random lasing like this. And with the increase of the pump, this random mode, the bandwidth will broaden and the mode superposition with each other. Finally, generate the uniform stable output. Output beam quality is also very good. So since this work, a lot of work has been done in related areas. While there's still an open question how to better control and functionalize the output. Actually, our ideas introducing functional components or special fibers into random fiber lasers. That is, to input the right thing at the right place to get what we want and to realize the effect 1 plus 1 larger than 2. Let's see the result we have achieved to control and optimize the output. In some of our work, we have introduced components into open cavity random fiber lasers to form half open cavity random. These components include point reflectors obtained by laser microprocessing and also tunable filters or time shapers like stereo gain absorber. Based on these devices, we can optimize in spectral and temporal domain. These are some of the results. You can see we have realized multi-wavelength tunable output, single wavelength tunable output, and bandwidth tunable or super continuum generation. So realized continuous wave lasing with very low fluctuation noise and pulsed lasing with tunable repetition rate. Well, this work focuses on single transceiver mode operation. That is, they do nothing with to control the output in spatial domain. We further use the multimode fiber into random fiber lasers. That is, we generated so-called multimode fiber mediated lasers. We have introduced multimode fiber or realized random fiber lasers and shaping the laser output through transceiver mode control. By doing this, we have realized spatial mode conversion, and we can tune the spatial coherency. We can also shape the output pattern to generate structured light. All these can be useful for imaging applications. Here are some of the results. You can see we have connected single mode fibers with multi-mode fibers by a liquid crystal cell, which can be controlled by voltage. By doing this, we can switch from fundamental mode to higher order modes. We also proposed and fabricated a single trench fiber with refractive index distributions like this. And this is very helpful to reduce the spatial coherency of the lasers. In third work, we have realized high-power multimode lasing in random laser. This power has been larger than 1, and the spatial coherency can be very low with spectral contrast less than 0.0. This is very useful for large vision imaging applications. The third part, say imaging applications. Two cases we have been. The first case is speckle-free imaging, or we call it direct imaging. That is, the light source illuminates the object, and the image is captured by the camera directly. In this case, the light source should have a low spatial coherency to reduce interference noise or to reduce speckle in the background. That is to realize speckle-free imaging. Secondly, the light source should better have a high spectral power density so as to realize long penetration depths. If too wide, the penetration depths cannot be very long. The second case, pattern-related imaging, or we call imaging through obstacles. In this case, the light source illuminates the object, and the image is obstacle medium, so the camera only gets diffused image patterns, but this image pattern includes the necessary information of the object. We can use some smart calculation method to recontrast the image. But there's a requirement for the light source is low spatial coherency, the same as the first case. And second, the bandwidth of the light source should be within the memorial effect decretion bandwidth. That is, different wavelength components of the light source should have same point scattering function in the. Let's see the performance comparison between the three topical light sources. Laser diodes, usually they have a narrow bandwidth and their spatial coherency is very high. So they will induce strong speckle noise and they cannot be used for two cases. Well, ASE sources, they have a low spatial coherency and they have bandwidth. In this case, they can be used for speckle-free imaging because their bandwidth is large, so their penetration depth is short, cannot be very long. And this exceed the memorial effect decrease bandwidth. So they can only be used in the first case and cannot be used for the second case. While our laser, multi-mode fiber mediated lasers, They have low spatial coherency and they have moderate bandwidth, so they can be used in this. Let's see some of the research result for imaging applications. First, let's see speckle-free imaging. The first case, the setup is like this. We have used the multimode fiber mediated random lasers. It's used to illuminate the sample, and the image of the object is captured directly by the camera. Let's see the comparison between the three types of lasers: ASE spectrum, LD spectrum, and ARM lasers spectrum. Their output field distribution, you can see ARM laser and ASE, their distribution are quite uniform. Well, LD laser, the output show obvious speckle noise. When we use them for imaging application, you can see out here, ARM laser and ASE laser, an ASE source, they show speckle-free imaging, while LD, you can see the output have obvious background noise, the speckle noise. We further compared our light source with ASE, a strong absorption medium. You can see the imaging of our lasers have a better contrast than the ASE source. This is because our laser can penetrate into a deeper medium. The penetration depth of laser, penetration length of laser is large. Actually, we have used this imaging method for dental imaging applications. That shows the image. You can see our laser, ASE source, they are speckle free, and the L it have a strong background noise, and a detailed comparison our result and ASC source. You can see this data, the data across this line reflects the mineral density, and this line corresponds to the cracked region. You can see our laser correspond to the blue curves. It have a better contrast than the ASE. We also compare result with currently used hospital use method like X-ray and microscope. You can see the data across this line. Our laser have a better contrast than the other two methods. Besides, our result can reflect the mineral density distribution in a same region, but X-ray or microscope, they can only separate different regions. They cannot reflect the mineral density distribution. The third because our laser works at the near-infrared wavelengths, so it is non-ionizing, which is very healthy to operate. Let's see some of the research results. The case that is pattern-related imagine through obstacles. The setup is almost same like the first case. We still use the multimode fiber mediated random lasers, and this output is used to illuminate the object, and the image is diffused by a obstacle medium, and the camera only gets the diffused image patterns like this. Actually, this diffused patterns include necessary information that we can build the autocorrelation function of the image. Based on this autocorrelation function, we can recontrast the image through a phase retrieval method or some smart calculation method. Well, there exists a problem because the upright image have the same autocorrelation function, so we cannot determine which one is true. To overcome this, we propose a two-step image method. Firstly, we use the light source to illuminate the upper part of the object, and when the image appears at the upper half of the pictures, it is true. When it appears at the lower half, it is not true. So by doing this, we can also recontrast the lower half of the image, and then combine the upper and the lower together. We can generate the true image. This is the imaging through obstacle. Actually, we have extended this method to realize multi-object imaging through obstacles. To do this, we first developed wavelength tunable multimode lasers. That is, when the laser output at different wavelengths, they will generate output patterns with uncorrelated with each other. That different wavelengths generate different uh, illumination patterns influence with each other. So we can multiplex them together to realize multi-object imaging. You can see from these figures, when the wavelengths scan within band A, this band A, and the light source only lightning object 5, and we can use the multiplex speckle to recontrast image 5, and when it scans in band B, the laser only lightning object 4, and we can use the multiplex speckles to contrast image 4. Similarly, when it scans within band C, we can recontrast image 6. That is, multi-object imaging can be realized through wavelength-sensitive speckle multiplexing. Well, let's come to the conclusion part. In summary, we have realized a multifunctional light source, the multimode fiber mediated random lasers. They can be in spatial, spectral, and temporal domain. Based on these multifunctional light sources, advanced imaging method has been proposed to realize speckle-free imaging and to realize imaging reconstruction through obstacles, and also multi-object imaging through obstacles. Okay, content. Before finishing, I'd like to thank my students and the colleges in UESTC, and also the project support from NSFC and the 111 project. Okay, that's all. Thank you very much for your listening.